I guess you see my screen.
Yes, sir.
Okay, great. So today I'll be covering the topics mostly in statistical thermodynamics. And as you have noticed that I have put a number 3, so we'll have 3 classes on this part. First one, today I'll be teaching about the distribution functions, ensembles. Then next 2 classes, I'll discuss more about partition function, phase space, and then slowly we'll move to molecular dynamics and molecular modeling and dynamics. Okay, so statistical mechanics or statistical thermodynamics. Okay, so I wanted to start with this slide. It's scary, it's interesting, it's something about the history. And if you read first 3 lines, then probably you get scared of studying statistical mechanics. So Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. So he hanged himself. Paul Enfest, carrying on the work, similar work. I mean, he is the postdoc of Ludwig Boltzmann, or the student of Ludwig Boltzmann. He also died. He shot himself in 1933. And now it's our turn to study statistical mechanics. Okay, so be careful. Anyway, jokes apart, I mean, those days were very different. It was full of scientific evolution, and many things happened simultaneously. So there are a lot of anxiety and depressions and competition and rivalries. Many things happened in that era. So there is a famous book or very popular book which is called, if you see on the right hand side, it's called Anxiety and the Equation. It's written by Johnson, Eric Johnson, and it's about Boltzmann life and what happened at that time. Why did Boltzmann? What were the contributions of Boltzmann? Why did he hang himself? Like something like that era. You'll get an idea. So this book is expensive, but if you guys come to my office next semester, I might have a copy of this book, so you can borrow it from me and then have a quick read and then return me. So again, so this paragraph I copied from another book. It's called States of Matter by David Goodstein. So the first chapter, first paragraph, he starts like this. Okay, to warn everyone, whoever is interested to study statistical mechanics. But now the next paragraph is more, positive, on a positive note. So perhaps it will be wise to approach the subject cautiously. We'll begin by considering the simplest meaningful example, the perfect gas, in order to get the central concept sorted out. In chapter 2, we'll return to complete the solution of that problem, and the results will provide the foundation of much of the rest of the book. Okay, this is positive. So let's start with this note, and starting with a simple perfect gas, how we can correlate with our thermodynamics and statistical thermodynamics concepts. Now I keep on showing this picture to just to put your mute. Pranjul, excuse me. Okay. Okay. So I go back to the slides. So far we studied thermodynamics, where we didn't talk about any molecular picture or mystic details. So there we talked about the thermodynamic states and thermodynamic variables. From there, today we'll be talking about mostly about the ensemble of molecules, a collection of molecules, which is the heart of the statistical thermodynamics. Then we'll again zoom into the system and pick out one water molecule, and then we go reverse. So starting from one water molecule, how we can model a let's say chunk or small portion of water, and from there how we go back to bulk water and get the thermodynamic properties. So it's a reversible process, thermodynamics to molecular modeling to thermodynamics. So, and this is the whole theme of this course. Now, as the good Stein books suggest, that let's start with a perfect gas. Okay, that's the simplest possible description of a model system. Now, before going to, let's say, the main topic of statistical thermodynamics, let me give you some idea about probability distributions, because these are very important for constructing the statistical mechanical equations and understanding the main parts of it. So I think every one of you has experienced or played this dice, right? So there are 6 possible numbers. Okay, if you throw the die, and so you can have many numbers. Let's say you give 10, 20, 30 trials, and then you try to plot a histogram. That means the distribution of the numbers, occurrence number of times a particular number occurs, that you plot as a function of that number. So you'll get a distribution like this. So this is again 15 trials, and you get these numbers 3, 4, 6, 5. So you put it there and plot them. So by looking at this distribution, what can you tell? This is a uniform distribution, right? Anyone? Do you agree with me?
Can
So
you
that means,
repeat once?
so let's say you have 15 trials, or let's say 10, 20 trials. Then what you do is you count how many times 3 occurs, or how many times you have 3, number 3 appeared. Then you put it there. So on the y-axis, you plot the probability or number of times that particular number 3 occurs or appeared. Similarly, the next one, you count or you focus on number 4, and you count how many times it appeared trials. Then you put it on the y-axis. So doing this, you get a histogram. Do you get it?
Yes, sir.
Yes, sir.
Okay. So now, by looking at this plot, you can understand that this is a kind of uniform distribution. So that means the probability of having these individual numbers is almost same. And do you think it will be like this if you increase the number of trials? Anyone? So I give you the answer. If you increase the number of trials, then the distribution will change. Okay. Now I want to tell something more than increasing the number of trials. Let's say instead of 1 die, you have 2 dice. And now what you do is you count, so you sum them up. Let's say you have number 4 appeared on the first one, and number 2 that appeared on the second one. So you sum them up, you get number 6. Okay. So now what you have is 2 independent dice. You throw them, and so there are 2 random numbers or random variables, right? In the first one, you have only 1. Here you have 2 independent random variables or 2 independent events, and you sum them up, then you get a number. So let's say the first one is 7. Okay. Second one is 11. The third one is 6. Fourth one is 11 again. Okay. So the minimum number in this case would be 2, and the maximum would be 12, right? Then if you plot these numbers as a following the similar protocol as that of the previous one, then you get a distribution that looks like this. And can anyone tell me why this number 7 has the highest probability? Can anyone guess?
So maybe because maximum number of combinations gives 7,
Yes, perfect.
like 2 and 5, 3 and 4,
Yeah,
and
yeah,
so on.
exactly correct. So the number 7 has a unique property, like you can have maximum number of combinations. As you go to, let's say, the list, the number 2 can appear or can occur only with one combination. So that is 1 plus 1. Again, the highest number, which is 12, can occur only in one combination. So that's 6 plus 6. So the numbers in the middle might have, the number in the middle has the highest probability, which is 7. Now, again, I have like a finite number of trials here, let's say 10, 20, then you get this kind of distribution. If you increase the number of trials, so let's say you throw 1,000 times and you plot them, then you'll get something like this kind of a distribution. Okay, and here notice that I have, instead of 2 dice, I have 4 dice. So what you did here is you increase the number of independent random variables and then you sum them up. So you start with 1 die and then you go to the 2 dice, then you have 4. So you are essentially increasing the number of independent random variables, and you do the same exercise and you are approaching towards a distribution. Can anyone guess or name, if you know the name of this distribution, can anyone?
Sir, normal probability curve.
Yes, it's a normal distribution. Okay. So it looks like a Gaussian, if you have heard of this word, Gaussian. Now, so this is an example to understand kind of a probability and distribution. Then there is another example. Let's say, again, I copied this example from this GitHub page. You can look at. So this is an interesting exercise or experience, I must say. So in this particular exercise, there were like 1,000 candidates. Okay, let's say we have 1,000 students, and I give one coin to each of the candidates, each of the students, and ask them that you flip them, so you get head or tail. So depending on head or tail, you can have a move left and right, and you can go up to, let's say, 0 to 1 meter left or right. Okay, so you start from this point. Do you follow my mouse cursor? So you start from this point, the origin, and then I asked everyone to flip the coin at every move and take left or right, depending on you get head or tail. And then if you do 15 steps, 15 such steps, and then you go from this part to the end of this part. And then eventually, if you follow the trajectory, like one highlighted in red color, then you will see at the end of the 15 moves or 16 moves, you have a distribution which looks like normal distribution. Again, this is a real life example. And if you want to do, you can do by yourself. You call your friends and try to do this on a ground. But it would take a little bit of elegant demonstration. So this
So
is
what the
another kind of, yes.
so what the position is mentioning 0 minus 3 minus 3? What does it signify?
Okay, so this is left and right. So there is nothing like the sign. You take left and right. Depending on that, you have this negative and positive. Okay.
Okay.
Yeah. So these are the real life examples of distribution and probability. Then, as I told you, this normal distribution, there is a name. You can call them as normal distribution, or there is a particular name. It's called a Gaussian function. So which looks like this, where sigma is the kind of a spread or width of the Gaussian, and x is the variable, and mu is the mean of that particular variable. When you plot them, they look like this. So again, as sigma decreases, so then you essentially decrease the width. So if you play with this number, then you see the Gaussian curve changes its kind of shape. Now I want you to try it by yourself. There is one software or website called desmos.com. So you can write the equation. Okay, so you can really edit this part, and so I have already written down. So you write here I didn't write the normalization of the pre-exponential term. I just put exponential minus x squared by 2a squared just to simplify this. Then so we have one parameter here. X is a variable again, a is a parameter. So you give the value of the parameter and you give a range. Here I give 0.1 to 1, and then I want to demonstrate that how this change depending on this number, how the Gaussian curve changes. So I play this animation, and as you see, as you increase, then the width of this increases. Okay, so you can go to this desmos.com. You can write down any equation, and if you want to see the plot, so they look like this. You can zoom in, zoom out, and you can do all sorts of. You can experience everything. Okay. Let me go back to the slides. Then